Hi everyone, welcome back. In our last video, we dive into the multi-head attention mechanism. Today, we are going to build upon it and construct a complete transformer encoder layer by adding the feedforward network, normalization, and residuals. Let's get started. A transformer encoder layer consists of two main sublayers, multi-head attention, and a position-wise feedforward network. Both of these sublayers are followed by layer normalization and residual connections. The multi-head attention mechanism enables the model to focus on different parts of the input sequence simultaneously, learning unique patterns and relationships. After the attention mechanism, we have the position-wise feedforward network. It's made out of two linear layers with the root activation in between. The first layer expands the feature dimension to a larger size, and the second layer brings it back to the original size. This network boosts the model's ability to learn more complex patterns and relationships. Layer normalization is applied after each sublayer to keep training stable. It normalizes features across all positions, making sure the distribution has zero mean and unit variance. This prevents the model from having gradients that are too big or too small. Problems known as exploding and vanishing gradients, which could otherwise make training really unstable. There are two common types of normalization, batch normalization and layer normalization. Batch normalization normalizes features across a batch of samples, ensuring that the mean and variance are consistent within a batch. Layer normalization, on the other hand, normalizes features across the feature dimension for each individual sample, making sure that each sample has a normalized distribution. Why use layer normalization in transformers? Batch size and sequence length can vary a lot, which makes batch normalization tricky. Instead, layer normalization works better because it normalizes each sample on its own. Plus, it's great for models using attention since it helps stabilize training with different input sequences. Residual connections, or skip connections, directly add the input of each sublayer to its output. This makes sure gradients flow smoothly through the network, preventing vanishing gradients and letting the model learn new features on top of existing patterns. To understand why normalization and residual connections are so important, let's briefly explain what vanishing and exploding gradients are. Vanishing gradients are like when you are trying to push a car up a steep hill but just can't seem to get enough momentum. The updates to the model's weight are so tiny that it barely learns anything. Now, exploding gradients are the opposite. It makes your car's brakes fail while going downhill. It starts speeding out of control. That's what happens when the updates are too large. They can cause the training to crash or lead to really erratic model behavior. Layer normalization ensures the gradients remain at a manageable scale by normalizing features across positions. Residual connections provide a shortcut for gradients to flow through the network without shrinking or exploding. With this understanding in mind, let's see how each component is implemented in the transformer encoder layer. To briefly recap, here's the multi-head attention class we implemented in our last video. If you haven't seen that video, check it out in my channel. Now that we have our multi-head attention ready, let's move on to the position-wise feedforward network. The feedforward network consists of two linear layers with a root activation in between. Let's write the code. Let's put it all together into our transformer encoder layer. We will use layer normalization and residual connections along each sublayer. First, we have the multi-head attention mechanism. Next, we have the position-wise feed-forward network. Layer normalization follows each sublayer to stabilize chaining. Apply the multi-head attention mechanism. Add a residual connection and normalize. Pass through the position-wise feed-forward network. Add another residual connection and normalize. And that's our transformer encoder layer. Finally, let's build the full transformer encoder using multiple encoder layers. We will define a class called transformer encoder and create a series of layers. Now that we have our transformer encoder implemented, let's test it by passing a sample input through it. First, let's define the embedding dimension. Next, we define the number of attention heads. Then, we set the dimension of the feedforward network. Lastly, we define the number of layers in the transformer encoder. Let's create an instance of the transformer encoder using these parameters. Now, let's assume a random input X with shape, batch size, seek length, D model. Pass this input through the encoder. Finally, print the shape of the encoder input and output. And there we have it, a complete transformer encoder. In this episode, we learned how to build a full encoder layer using multi-head attention and feedforward network. And we also discussed the importance of layer normalization and residual connections. Thank you for joining me today.